At GNS Science in New Zealand for 10 years as a volcano geophysicist, so we won't hold that against him, where he led the team that modernised New Zealand's volcano monitoring capability, including designing and implementing new seismic, geodetic and remote sensing networks. He began his career working in mineral exploration and mining geophysics in Australia and New Zealand, which included 2.5 years for BHP after graduating with an MSc from University of Auckland. Welcome, Greg.
Okay, so this is something slightly different from the talks we've had this morning, using the same techniques and data sets, but applying them to a different scenario here, this time for natural hazards. So I'm going to be talking about Mount Tongariro in New Zealand and the internal structure and volcanic hazards that we've been thinking about with that from gravity and magnetic data and models that we've produced from there. So this is part of a paper that I was published earlier this year in the Journal of Volcanology and Geothermal Research, and if anyone wants a copy of that, you can see me afterwards. And I'd like to thank MyTax and Mira Geoscience for helping sponsor my studies. So the motivations for this study: volcanic hazards impact people living both near and far from the volcanoes. Things like ashfall can affect regional and global air travel. Things like earthquakes, lava, pyroclastic flows, lahars, landslides affect people locally. A lot of codes out there that model and try and forecast these hazards require some like realistic properties to be input into them, but often these properties are unknown. So many of these codes operate in like a half space, which obviously isn't that relevant. So what we're trying to do by improving our knowledge of volcanoes' internal structure is important for many aspects of hazard monitoring. And I'm just going to run through some of these hazards that are applicable and going to kind of think about in terms of our gravity and magnetic models later on. So this is actually Mount Tongariro here. Oops. Mount Tongariro here, Ngarahoe and Ruapehu in New Zealand. You can see there's these big faults cutting across the flanks here. We're interested in what's the relationship of these faults to the basement structure and to any vent locations. So do these faults control where eruptions might occur in the future? There's a big hydrothermal system at Mount Tongariro, and these hydrothermal systems are quite spectacular. They make nice lakes, people like to go and walk there, but they can often result in really hazardous explosions, such as what happened in Japan at Mount Ontake a couple of years ago, and also at Mount Tongariro in 2012, which we'll talk about a little more. So knowing more about the extent of the hydrothermal system is important. Hydrothermal systems also chemically alter and weaken the rock and can promote landsliding. And in fact, a landslide was a trigger to the 2012 eruption from Tamari. And this is, you can see the landslide came down this valley here, and these are the explosion vents that resulted. As I mentioned earlier, many models that try and model the volcanic unrest processes, such as seismicity and so on, they often just work in like a simple half space or maybe just a 1D model. So therefore they're kind of limited in the accuracy which we can interpret monitoring data. So you often see diagrams such as these in papers where we've got our volcano and the active processes in here, but really we're kind of interested, well, what are the properties of these rocks around here, because they will affect, say, the contrasts from the conduit to the host rock can be important for modeling like seismic waveform properties and so on. So we're trying to fill in these kind of question marks here. So the aim of this study was at Mount Tongariro in New Zealand, and it was really to delineate three things. One was the basement structure under the volcano, followed by what's the internal structure of the distribution of the volcanic rocks above the basement, and also what's the extent of the hydrothermal system. And while we're looking at these, we're going to be thinking all the time about the volcanic hazards that we can derive and understand better from our models. We're going to use gravity and magnetic data modeled with, in this case we're using VPNG and GoCAD, which gave us some advantages over just a constrained version, as we'll see later. So this photo in the background is actually Mount Tongariro Massif. We've got Mount Ruapehu in the background, Narahoe here, and then Tongariro is this kind of complex system of many vents. And this steam cloud here was the eruption of Tamari in 2012, and you can see that grey kind of ash is some of the deposit resulting from that. Just a bit of geography. New Zealand is down the bottom of the Pacific Ocean. We've got the Pacific Plate and the Australian Plate in the subduction zone plate boundary cutting through. That results in the Taupo Volcanic Zone, which is this big area of extension as this East Cape kind of rotates to the southeast. And that results in many volcanoes in this area. And this is Mount Tongariro at the very southern end of the TVZ here. A bit of geology. So this is the Tongariro Massif and color-coded by kind of different generations of volcanism. The volcano has been active since about 275,000 years ago, and these are the kind of groupings of the major sequences there. It's bounded on either side by basement greywacke rock over here, and you can just see a little bit of it in the green over here, and cut by these northeast, southwest stringing fault structures, which results in a kind of a graben basement low underneath the volcanics. So just a bit of a workflow of how we're going to tackle this problem. We've got our gravity and TMI data. What we're interested in is looking at both the basement structure, so the deep structure, as well as the volcanics. So we're going to look at some filtering of the gravity on wavelength to separate the shallow versus the deep. We're going to look at basically creating a forward model from the existing geology map, and then populating that with physical properties that we've got. And then we're going to run our inversion model to kind of refine the offsets on those faults, the physical properties within the basement. Then we're going to look at the full wavelength data for modelling what's above that basement. We'll get our basement model fixed, and then we'll basically invert for everything above it to look at the distribution of the volcanics. We'll do that with both the gravity and then the magnetics, and then we'll have our full model from which we can kind of do our geologic interpretation. So this is the regional gravity. The black dots are part of the New Zealand gravity database, and the red dots are ones that I collected, and blue dots were some older existing data on the volcanic areas. So you can see this is the TVZ here is this major gravity low feature, and this is the very southern termination of it here, where the strike kind of changes to this east-west. There's about 950 stations in this whole area. Then if we kind of zoom in here, remove a regional field, we can see much more structure from the volcanic areas. And the main vents are these white triangles, and we see a lot of gravity lows associated with these. A couple of them have highs associated with them, but mostly we've got this kind of low trough within these highs either side. So this is our basement outcropping on either side, and over here and over here. And then between these two fault zones, we've got most of the volcanics outlined kind of between. In terms of physical properties, by going through a whole bunch of older studies on the geology of this area, I was able to extract quite a good database of physical properties, which we can use to kind of help constrain our model. So I've got density samples, both wet and dry densities, in these histograms here for the different rock types. And we can see for this one here that the greywacke basement's pretty tightly confined at around 2,700 cubic meter. The andesite lava samples span quite a range, as we'd expect, depending on the degree of vesicularity. And pyroclastic samples, again, quite a range, generally a little bit lower density than the lavas. As we'd expect, these are like scorias and very vesicular rocks. There's a minor sedimentary unit in here, which is just a thin thing which we don't really, we can't really resolve in our model. And then in terms of mag-sus, the main thing is that the basement's non-magnetic, so that's an important contrast for when we're trying to map the extent of the volcanics based on the magnetics. And then there's kind of varying degrees of susceptibility of the lavas, which are generally slightly more magnetic than the pyroclastic material. So to try and do separate the basement from the surface effects, we're looking at some wavelength filtering. And so spectral analysis, calculating the power spectrum of the gravity Bouguer anomaly here and the magnetic anomaly here. And just by doing some curve fitting, we can kind of come up with these estimates as ballpark of the depth of these interfaces. So in the gravity, we've got like a two-layer case with the volcanics overlying a basement at around 0 meters above, well, at around sea level. And again, with the magnetics, we have this kind of interface at around sea level as well. The elevation of the volcanics here varies from about 1,000 or 1,500 to 2,200 meters above sea level. So there's potentially 1.5 or so kilometers worth of volcanic material above the basement. And by looking at these curves here on the gravity, the top curves are kind of a corrected curve required to calculate these depths, but the bottom curve is the raw spectra. We can see changes in wavelength at around 10,000 and 3,000 meters. So we did a couple of trials with wavelength filtering around those numbers and chose the 10,000 meter filter for the gravity to start with. So to construct our model, like any kind of diagram, we drew a few scribbles on a whiteboard and kind of came up with a conceptual model, transferred this into to GoCAD, where we had our basement outcropping on the side here, also just outcrops, you can't quite see at the very corner here, put in the faults and kind of gave a couple of guesses as to the likely throw on these faults based on geologic mapping people have done elsewhere. So we used this as our starting model, populated it with the densities from our physical properties, and went from there. So this is the low pass filtered gravity signal. So we can see we've removed the shallow effects of the volcano, and we just want to look at the basement changes underneath that. And this is actually the final gravity, the final inverted model. So what we did here was a mixture of a combined geometry and property inversion, where we're adjusting the height of the interface up and down, and with alternating that with a property inversion. So we're kind of doing alternating steps of geometry and property to come up with this best fit. Now, we did originally just a geometry inversion with a homogeneous density, and that gave a pretty good result. But then we thought, well, let's see if we can pick out any subtle contrasts within the basement, because the basement terrain on this side is a different group of rocks to the terrain on this side. And you can see there is a subtle contrast, slightly less dense over here to slightly more dense over here, and that agrees with the petrology of those rocks, where this is a slightly more mafic unit, and this is a slightly more felsic in terms of the rocks that derive these sediments. And we can see here that we've got these faults here, and the throws on these faults are now something we can look at. So overall, there's about 500 to 700 meters vertical offset above the graben. If we say that this graben started subsiding around 275,000 years ago, which is the dates of the oldest volcanic rocks, then we can come up with these subsidence rates of around 2 millimeters or so per year. People who have looked at these faults have come up with rates of around 4 millimeters per year. So they're kind of similar in the right ballpark. And as I said before, that the basement density variation relates to the different terrains that are on either side of the graben here. So what we did now we've got our basement, we wanted to fix that in our model. So basically lay that into our model but set the cells not to be active. And then we're going to use the full wavelength of the data set and then basically solve for what's left. And that's going to relate to the shallower material above the basement. In this case we did a heterogeneous inversion because the volcanics, well, we didn't really have much guidance on trying to constrain them with the geology. You know, volcanic geology is very complicated and not nice layering or anything. There's many cross-cutting relationships. So we thought we'd just go with a heterogeneous inversion rather than try and create a whole bunch of stuff that we didn't know much about. So these are some different depth slices from 1,500 meters. The surface is probably around about 1,500 meters on average, going down 1 kilometer or so. So you can see these bits I've highlighted in yellow, if you can see them, some low density areas here and here, and within that there's this high density area here. I should say that these sections on the left are from a least squares inversion, and these on the right are from a stochastic inversion. And that kind of shows similar things, but obviously this is a much noisier looking model than this one. So tracking these features here, we can see them kind of persisting through these depth slices. This is coincident with Mount Narahoe, the big recent stratovolcano at the southern end of this massif. And as we go down deeper, we're losing a bit of resolution. But we still have this high gravity high here, which is here and here. And actually in the field, this actually correlates with a really big thickness of lavas that are mapped. So I suspect this is a event that's the lavas have been retained from here. In terms of what's around the faults, on here we've got mostly kind of lowish density around here. Down here there is a bit of high density associated with this fault zone. Again, there's quite a big thickness of lavas built up around here, so possibly this fault zone is related to an eruptive episode, but in general we don't see like big dense intrusions along these faults. Then looking at the mag data, this is compared to a lot of the data we've seen here, this is very low-tech mag data. It's pretty poor resolution. It was flown probably at constant elevation, but because of the huge topography changes, we've got probably between 200 to 1,000 meters actually above topography, depending where on the flanks of the volcano you were. So we've also been talking a lot about remnants today, and there's this big hole in the middle of the data here. But I'm pretty confident that because these rocks are only a couple 100,000 years old, that this is not related to remnant magnetization, but is in fact related to the destruction of magnetite through hydrothermal processes. And we'll talk a bit more about that later on. But you can see the mag kind of maps the general outline of the volcanics bounded by the fault zones here, and Mount Narahoe here is this strong mag anomaly. This is going to be partially due to the closer, this is a big high mountain, so obviously the sense is a lot closer to the terrain here than it is on the flanks. Again, this time we used, we brought our basement model in, but we know the basement's not magnetic, so we can fix that as like a lower bound on the magnetic material and just invert for what's above it. And we see this mag low here, here, kind of going down in all our slices. And this corresponds with that gravity low that we saw in the previous slides around the hydrothermal system. The flanks are moderately magnetic. We have some material over here which relates to lava flows that have come down the sides of the cone here. And then some stronger material here to the south, which persists kind of through the depth. So, yeah, the extensive hydrothermal, one question we're interested in as well, why is the hydrothermal system just here? and why doesn't it carry on down to the south? So Mount Narahoe, which occurs in the south area, is pretty young. It's only 8,000 years old. And if you look at rates of dissolution of magnetite, then it's just simply not old enough for fluid to have circulated through it for long enough to dissolve magnetite. To dissolve that volume of rock, you need that circulation to have gone on for 10 to 100,000 years. And so that gives us some idea as to the age of this hydrothermal system here, to have burnt this big hole through the magnetite. This hydrothermal system has to be pretty long-lived. So looking at our kind of combined models, just some isosurfaces of high density in here, with the red and low density here. You can see under Mount Narahoe, we've got this low density kind of route extending down to the basement. This correlates with this high susceptibility of this fresh volcanic rock, unaltered. It's low density because this is mostly a big scoria cone. Lots of pyroclastic material, not much solid thickness of lava. And then here, the low density in this red here corresponds with this low susceptibility region here, relating to the hydrothermal system. So some things we can talk about in terms of volcanic structure. We can look at the volume of the volcanic material above the basement, and people had estimated this previously based on the geologic mapping, but from our geophysics model, we can see that this estimate was probably underestimated, probably by 5 or 6 times, simply because they didn't have the basement depth well constrained. If we look at then some long-term eruption rates, we can derive a rate based on this volume over the last 275,000 years of around 1.3 times 10 to the minus 3 cubic kilometers per year. And that's pretty similar to the global andesite production rate, but it's several times larger than the rate that was previously estimated. So it brings it back into kind of more normal lines. This low density and high magnetic root under Narahoe, we're interpreting as a magmatic feeder system. This is going to be an area of highly fractured rock, as many intrusions have come up through it. It's very young, so it hasn't had time to alter, which gives it the high susceptibility. There's only limited evidence for those bounding faults acting as pathways for intrusion. There's really only maybe one area where we see there's a volcanic center with a high density that kind of corresponds with that. So generally think these faults aren't that important in terms of localizing eruptions, and the known high density areas, we can relate those back to thick lava flows that are observed in the field. So looking a bit more at the hydrothermal system, this is kind of these two isosurfaces of the density in blue and susceptibility. And you can see they're pretty well intertwined within each other. So the fluid circulating through here, there's probably 200 or 300 degrees. There's fumaroles out here, very gas-rich acid gases dissolving the rock, destroying the magnetite. So the hydrothermal system is defined by demagnetized and low density. It looks like, if we go back to that other slide, that that the system's actually bound by these faults to the east and west. So one of the interesting things about this hydrothermal system is that most of the surface features you see are kind of oriented in this north-east-southwest strike. We don't see any hot springs or anything off to the flanks to the east and west. And it's possibly because these faults are actually acting as some kind of barrier to the fluid flow in that direction. And yeah, Narahoe is too young to have developed any appreciable alteration. Even though there is hydrothermal activity there, it's only been going on for a few thousand years, so hasn't been able to do much. Finally, we can look at the landslide hazard. All this alteration creates mechanically weak rocks, so in areas where those slopes are steep, those are areas of potential failure. So this is a DEM, a slope-shaded DEM where the blue areas are steeper than about 30 degrees, and this red amoeba is the outline of the hydrothermal system from the graph and magnetic models. So these where this blue is inside this red is where we would infer that areas of landsliding are a hazard. And in fact, there's history of quite catastrophic landslides off here. Around 55,000 years ago, there was a big landslide from the northwest somewhere, and perhaps it took out this big chunk of, if you drew the line from here to here, this could be the source region of that landslide where all that materials has been, it's just slowed downhill. So the eruptions from 2012 were actually right on the edge of the hydrothermal system just here. And we could actually see in the class that came out of that there was a mixture of fresh and altered rock. So that kind of matches nicely with its position right on the edge of the system there. So in conclusion, we've been able to define a new basement model, which has led to a new kind of total volume of the volcanics, which is a higher magma supply rate. Within here, there's no real evidence for any like shallow magma chambers or anything. In fact, there's a recent MT survey I've done over this whole area which shows some conductors, but they're down at around maybe 8, 9, 10 kilometers depth, which is below what we can, it's below our resolution for our surveys. There's a magmatic plumbing system imaged under Narahoi from the low density, high susceptibility material. And it doesn't look like the faults are major magmatic pathways, but they might act as impermeable barriers to fluid flow. And they're probably low probabilities for future eruption sites. We've been able to delineate the hydrothermal system in areas of potential flank collapse. And one of the interesting things we can do from our density model is convert it to seismic velocity. And we've got now a 250 by 250 grid of seismic velocity values that we could use for earthquake location in the shallow edifice of the cone. And so when you're talking about volcanic unrest with, say, magma intrusion that's generating earthquakes, having an accurate velocity model to locate those earthquakes is very important in terms of getting the correct depth. So it's possible that the density model we could convert to the P-wave velocity at least and use that as a proxy for a velocity model. And that's all.
Thanks, Craig. Time for a couple of questions. Okay.
Is the lack of a shallow liquid magma chamber surprising to you, or?
No, not really. These systems often have maybe several zones of magma systems, so maybe at like 10 kilometers or 5 kilometers, and it seems like this system, they come from that depth and they don't really stop along the way up. So there isn't like anything sitting at like 1 or 2 kilometers depth. So the model we had for the 2012 eruption was for a dike injection, and it looks like it's stalled at the basement surface. So basically the density contrast, the density boundary was where that dike stopped, and that's about where the shallowest earthquakes were at that kind of 1.5 kilometers depth.
How long prior to the eruption was the seismic activity?
There was about 4 to 6 weeks of precursor seismic activity, and there was also, when the gas fumaroles were sampled, there was a really strong change in the gas composition. The concentrations changed like by orders of magnitude from the background values. So we're pretty confident then that there was some kind of intrusion going on, but we weren't sure exactly where it was or at what depth it was at. So.
Craig, I just make a comment. I think it's really important for us to see stuff like this. The geologists all the time go to New Zealand, go to places and study modern day hydrothermal systems so that they can understand exploration and how the hydrothermal systems that they mine or explore for are formed. And you don't really see it in geophysics too much where we look at a modern day system. And so, to me, it's some really good takeaways from that. And magnetite destruction around a thermal system is pretty well known, but the market decrease in density, to me, is something that I probably haven't considered and is a potential takeaway when looking for, especially low sulfidation epithermal systems. There might be another kind of diagnostic signature.
Yeah, I think you're totally right that by studying these active present-day systems, we can learn a lot about, you know, the ore deposits as well. So.
Right.
Have you taken the temperature into account? Because you know the volcano is either the density or the magnetic susceptibility will be affected by the temperature. So
yeah, the temperature of the hydrothermals, well, the temperature of the surface fumaroles is nothing hotter than 100 degrees. And so we think the temperature of like the gases inside the hydrothermal system are probably around 200, maybe 250. So that's like, well, it's obviously well below the Curie point in that terms, but that's going to be contributing in the long term to this magnetite destruction. It's acid gas. But no, I mean, I haven't taken it into account directly, any temperature directly in the modelling or anything, but it will be causing some of that destruction that we see.
Okay, that seems like a good question. So thanks, Craig, again.